In this video, we're going to talk about what an algorithm is and why we study them in computer science. First, an algorithm is a set of steps, we might call them instructions, that provide a procedure for solving a problem. So let's just go ahead and write out what the definition is. Now that we know what an algorithm is, it's a set of steps that provide a procedure for solving a problem. What do we mean when we say problem? When we say problem, we are referring to some general task that has input and needs something done to this input to compute a corresponding output. And now that we know what we mean when we say problem, we have to ask ourselves, what do we mean when we say general task? And the best way to describe a general task is to think about an example. Let's think about classical sorting problems. Say we have three numbers, A, B, and C. In this example, the general task is sorting. The problem we're asking is, how do we sort these three numbers? The three numbers are the input into our problem. So our goal would be to write an algorithm that solves this problem, which is sorting. Now, while the general task is sorting, these three numbers, they represent the input, but they also represent an instance of sorting, because these are just three numbers, and we can sort more than just numbers. We can sort strings, and we could sort objects. For example, if you have something that is in dates, if you're looking at dates, we could sort things by dates. For example, events. If you have some event happening in December and another event happening in November, we know that November comes before December. So if we sorted those events, November would come before December. It is important that I stress that we are able to recognize an instance of the problem. The, the problem we are trying to solve is a sorting one, and we're just looking at the specific instance. According to Stephen Sakina, author of Algorithm Design Manual, and I'm sorry if I'm pronouncing his last name incorrectly, but he says in his book, determining that you are dealing with a general problem instead of an instance is the first step towards solving it. And it's important to know that when we write algorithms, we should write them to be as general as possible. This means that we want our algorithms to solve any instance of valid input for the problem that we describe. Consider our three numbers again, a, b, and c. Let's look at a simple example how we would sort these numbers using some code. I'm going to go ahead and get rid of this. Just remember the importance of recognizing an instance of a problem and the general problem that we are trying to solve here. So I went ahead and pulled up a small snippet of some Python code. This is a function. I just couldn't fit this into the image without cutting everything else off. So we're going off our previous example. We're trying to sort three numbers, number A, B, C, and we're going to return a tuple, which is just an immutable array of three integers. So first things first, we're going to get our smallest of the three numbers. We're going to get the largest of the three numbers. And we're going to find the middle by adding all three numbers up, subtracting the smallest, subtracting the largest from the previous step, and that would give us our middle. And then we just return them in that order. Now, this would work. It checks out. But there are a couple of problems. What if instead of numbers, these were strings instead? Would we really want to write a separate algorithm for this input? What if there were more than three variables to sort? We would really be in trouble then because our program only accepts three arguments. So I hope with this example, the idea of a general task and why we want to write algorithms that are general is cleared up for you. So I hope this example clarifies why exactly we want algorithms that solve general problems versus instances of the problem. Now, while this small program does work correctly, it's only going to work correctly for that single instance, that single input. But we should be writing programs that handle any type of input and can even handle edge cases as well as invalid input. So now let's talk about the why. I'm going to go ahead and make some room here and clear all this space up. In math and computer science and many other areas of study, there are typically multiple ways to accomplish the same task. But are some ways better than others? In computer science, the answer to that is a resounding yes. For example, let's pretend we have a sorted array of numbers. And let's also say that we have some target value, maybe call it 6. So we want to go inside of this array and look for this specific value. And there are several ways that we could do this. And before we begin, go ahead and pause the video and see if you can identify what the general problem is and the instance. Well, looking at this problem, we can see that the instance is the array itself. It's the specific input to our problem. Now, what is the general problem? The general problem is going through a sorted array and looking for a target value. Now, this could be a different array with a different target value. This could be a lot bigger, smaller even, maybe even empty and have no values. And we want our general algorithm to work on all of those cases. So now that we know the instance of the problem and the general problem itself, searching through a sorted array looking for a target value, how might we solve this problem? Again, go ahead and pause the video. So now that we know the instance and now that we know the general problem at hand, going through a sorted array and looking for a target value, determining if it's present, how might we go about actually implementing this and solving this problem? And again, there are a few ways to do this. For example, we could start at one end of the array and then go through each element until we find our value. And we would get right here and say, yes, this is true. We found our value is right here in the array. And if we were to write some code like that, it would look something like the following. As you can see, we take in a list of numbers. This is a lot better than going just for this specific instance. This can take in a list of an empty list, a super big list, doesn't matter. And then this can take in any target value. And then we're going to return a Boolean, whether the value is present in the array or not. So what we're going to do is we're going to go through this array. We're going to look at each number in the numbers. If our number is equal to our target value, we'll return true. And if we go through the entire list and the value is not present, we'll just go ahead and return false. So this algorithm works great. We take in a list, we can go through the list, we can find our target value, and we are accomplishing the general task, general problem at hand. But what if our array got super big? I mean really big, like millions of target values to test. Now, our algorithm would work for it, but there's a couple problems. Now, let's pretend for some reason that finding this target value is super important to us, and we want it to be done as quickly as possible. This is one of the major reasons that we study algorithms: efficiency. Currently, how we are approaching this problem is we are looking at each value one at a time in this list until we get to the end of the list. It's great, it works, but can we do better? Can we make this algorithm faster? If you haven't learned it yet, this is a linear algorithm, pretty much meaning that if we were looking at a graph, as our input grows, the rate at which our algorithm can solve this problem is constant. So as the amount of values increases, as this array gets bigger, the rate at which we can solve the problem remains constant. So you add in another value, you're going to add in another step just to check. So each value that you add, you just go up at a constant rate. And we'll learn more about that in a future video. Up here in the top, I'm going to keep track of the reasons why we study algorithms. We know that we want to make this algorithm more efficient. In other words, we want to find our target value as quickly as we possibly can. How might we do this? I'll go ahead and get rid of this. Go ahead and pause the video and see if you can come up with something faster than this. Well, brainstorming some ideas. What if we had 2 pointers instead of 1? Generally, you'll see often that when you have a sorted array, often a trick you can use to accomplish the general problem at hand is using a left and a right pointer. But back to our problem here. What if we had 2 pointers and at each iteration we compare their middle value? So let's go ahead and mark out these indexes. 1, 2. So now we go ahead and find the middle value. So we'll do 0 plus 5 divided by 2 is 2.5, which will integer division will land us at 6. And just like that, we found our target value. This was the middle. And this was a lot more efficient. The algorithm that we just described runs in log of n. And remember that our previous algorithm runs in O of n. Let's go ahead and look at a chart and see how these two values compare. Here we can see this is our, let me use a different color. This is our first algorithm, It's linear, and it looks great. As you can see, there are a lot of not so great algorithm implementations out there. But down here, we have log of n, and log of n is extremely good. The only thing better that would be constant time. But log of n is still very efficient. So we can see that log of n takes less time than our linear algorithm from before. So let's go ahead and clean some of this up. And again, if the big O notation doesn't make sense yet, there will be a future video where we will look more into it and get a better idea of what an understanding about what it is. So how would we implement this in code? Let's go ahead and take a look. So again, we have our function definition. We're searching for the value as present. We have our list, and we have a target value, and we're going to return a Boolean whether this value is in fact in our array or not. So we're going to set up our left and our right pointer, left starting at the beginning of the array, and the right pointer starting at the end of the array at the last element. Now while left is less than right, so while these two don't cross each other, we're going to get the middle value, and this in Python just means integer division. So when we added up in our example a few seconds ago, 0 plus 5 divided by 2, instead of getting 2.5, which is a floating point, which doesn't make sense for indexes, we got we floored it down to this 2. And then going forward, we're going to see, okay, is this value equal to the target? If it is, return true. If the value is less than the target, that means that we need to get a bigger number, so we will increase our left pointer. And otherwise, if it's not less than and it's not equal to the target, it must be greater than the target, so we will decrease our right pointer. And if we make it through the entire list and we don't find our value, we will simply just return false. Great, this looks fantastic. This algorithm allows our pointers to step over multiple values at a time, saving a lot of steps, reducing our complexity from O of n down to log of n, as we just saw. And this is much more efficient than our previous algorithm. But there's one problem. And if you have some coding experience and maybe you've done some LeetCode problems, you might be able to see the problem in this code just looking at it. Go ahead and pause the video and walk through it and see if you can spot it. Let me ask you this. What if we have an array and it has one value? Just say 1, and our target is indeed 1. Well, our left and right pointer, they're both going to start here. But the moment that we get to our while loop, left is equal to right. So this whole entire portion of code will never execute, and it would just immediately return false. But this is undesired effect because our target value is indeed in our array, but our solution, our algorithm, it's not correct. Which brings us to our next important reason why we study algorithms, which is correctness. So how would we improve this code? Well, it's actually very simple. We would just be checking for less than or equal to right. So now when we enter this code, we would say, alright, 0 plus 0 divided by 2, well, that's always going to be 0, and that's our mid value, and it is indeed equal to target, so we would return true, and our algorithm is now correct. And the third and final reason that we study algorithms is we want algorithms that are easy to implement and understood by our fellow computer scientists and algorithm enthusiasts. This doesn't look that great. I can go ahead and erase this stuff because we don't need it. So these are the 3 reasons that we study algorithms. So now that we understand that algorithms are a set of steps to solve a general problem, we also know what an instance of a problem is. We also know that we study algorithms to write more efficient, correct, and easy to implement instructions. So how do we know how efficient our algorithms are or how correct they are? This is where the analysis of algorithms and the use of proofs come into play. In the next video, we'll review important proof concepts. I hope this video was helpful, and until next time, thank you.